All right, so this is an impulse change in momentum question, a typical physics level question. We have a baseball that's being pitched at 42 meters per second. The batter then hits the ball horizontally toward the pitcher at 58 meters per second. Find the change in momentum is the first part, and then trying to find the average force during the contact if you know what the time is. So let's attack the first part of the question based on the information that we have been given. So we know that, so we're looking at part A. We're going to do a different pen here. Okay. So we have our mass of the baseball is 0.145 kilograms. We know that the initial velocity is 42 meters per second, and we know that the final velocity coming back towards the pitcher is 58 meters per second. And we're looking for the change in momentum or the change in P. Now, the issue with this is that if you just write down this information as it is and don't really think about it, then you're going to miss a huge point. And that is the baseball is going this direction initially. Let's just say this is our initial velocity is going this direction, and then our final velocity is actually going to be going back towards the pitcher. Okay, so these are totally different directions, so they can't have the same sign. So we can designate right as positive and left as negative because it doesn't say where the pitcher is located. So if you were to draw it out, you know, here's the ball's getting released and you draw it this way, you can say that way is right, is positive, and this way back is negative. So that's what I'm going to do for mine. If you do it differently, you'll get the same magnitude, but you'll just get a different sign, which is fine. So you've got your positive, negative, and then this is again what we're still looking for. So let's set it up. Our change in momentum is going to be equal to our mass of the baseball times the change in velocity of the baseball. Right? The baseball's mass is not changing, so the way that the momentum is changing, if momentum, MVP, is equal to the product of your mass times your velocity, if your momentum is changing, in this case we're looking at our velocity changing, mass typically is not changing, but our velocity can more easily change. So we can say our mass is, so let's just do it like this. Change in V is really VF minus VI. And then let's take it another step. Let's plug in. So we have our mass. We have our final, negative 58, minus our initial, right, which is a positive 42. Okay. So our change in momentum is going to be, this is 100 meters per second times 0.145, and that's going to be a negative 14.5 kilograms centimeter per second. Okay? That is how the momentum changes. And it changes more in favor of the negative direction because it comes off the baseball bat with a greater velocity. So you have a greater shift towards that negative direction as we have it defined. Okay, that's why that's a negative. If you defined it the other way, this was positive, this was negative, you'd get a positive 14.5. Okay, because your greater difference would be in the positive direction. So that is A. So let's look at B. If the ball and the bat are in contact for this amount of time, so this is T, what is the average force during the contact? So we're looking at F. So F is what's in question. We have T given to us. And we do know change in P is this, right? Negative 14.5 kilograms centimeters per second. So we know from our impulse change momentum equation that Ft, right, this is really Ft equals change in momentum delta P, or delta M delta V, right, or delta P, same thing. All right, so we're going to use that for over here. So we're going to say Ft equals change in P. So we're looking for F, so we isolate it, divide T on both sides. So we have force equals our change in P divided by T. F equals negative 14.5 kilograms per meter per second divided by our time. Now do the seconds cancel. Right, we can do the math fairly easily and get negative 31,521.74 newtons. Okay, let's see why that's a newton. Let's just look at our 2 units. So we have, let me pull it out over here. So we have kilogram times meter per second over second. And some students will say, oh, this cancels, so we have kilogram times meter. Well, let's reciprocate it. So we take our numerator times the flip of our denominator, and you will see that kilogram times meter times 1 goes on top. On bottom, it's second times second, which is second squared. So kilogram times meter per second squared is a newton. And of course, we are looking at force, and so that makes sense.